a intramolecular aldol substrate. And we have several different options for which proton can actually act as the nucleophile, so which protons are moved. We have this proton, this proton, this proton. So since these are all acidic protons, we can form an enolate by deprotonation of either one of these. And so that gives us 4 different possible products. But what's the thing I keep saying about the aldol cyclization that makes it more simple than it actually is?
Find the 6th ring.
Yeah, you're going to get the most stable ring system. And so you're either going to get a 5-membered ring or a 6-membered ring if you can. Any aldol cyclization that give you a 4-membered ring are just going to pop back open through a retro aldol and give you your stud materials. So instantly, you don't even have to draw this out. You can just say, if we form the enolate here, so minus charge here, 1, 2, 3, 4-membered ring, not going to happen. If you deprotonate this hydrogen here to form the enolate of this carbon, again, and it attacks this, we have 1, 2, 3, 4, 4-membered ring, not going to happen. So just from that, we can say this won't go and this won't go, so we now have it down to 2 options. This hydrogen and this hydrogen. And again, we're under completely thermodynamic conditions, so either one can form, but one's going to be more stable than the other. So I'm going to draw both possible aldol products, and you're going to tell me which one you think will be more stable. So if we deprotonate this one, time so you guys can really walk through this with me. We will form this enolate which can attack here. Giving us an intermediate that looks like this, so a 6-6 ring system. Which then can of course be protonated. To give us our aldol product. And of course we're under basic conditions. And so under basic conditions, if we heat the reaction up, the aldol will go all the way from just the aldol reaction to the aldol dehydration. So under basic conditions, if you heat it up, the aldol dehydration will go all the way. So it won't stop at the aldol product. At room temperature, it will stop at the aldol cyclization product. But if you heat it up, it will go all the way to the dehydration product. Give us the enolate. Sorry to give us an enolite. And then we can do our E2-like mechanism. Kicking up OH minus. And again, since we're under basic conditions, so ETO minus, kicking up HO minus isn't going to be that big of a deal since we're swimming in sodium methoxide. And sodium methoxide and sodium hydroxide are very similar pKa-wise. And so if you're swimming in base, it's okay to kick off hydroxide. Only when you're swimming in base though. And so then that will give us our final Robinson annulation product, or a possible Robinson annulation product. So the full Robinson annulation product here. A couple things I want to point out before I go into the other possibility, and then let you guys tell me which one you get. So this guy right here, is this a chiral center? It is. And so that means when we attack this, is it going to attack the carbonyl on this ring from the same face? It's pointing or from a different face. So just let me throw out one of the enantiomers of this. So if we have this, for instance, this enantiomer, so this H is pointing towards us, and this, and the enolate's pointing away from us, so pointing to the back. Will this attack from the back face or the front face of the carbonyl? It will attack from the back face. And so pretty much what I'm saying is, we have our carbonyl, and so if this is our carbonyl, if the enolate is pointing towards you, it will attack like this. If the enolate's pointing away, it will attack from the back face. So it will attack the carbonyl from the same face that it's pointing towards. So just to show you, so in this case, if this is pointing away from us, it will attack this carbonyl from the back face. So that would mean, so this hydrogen's here. That would mean that this bond forming would be pointing away, meaning that the OH would be pointing towards us. And so basically, what we get in this reaction is the O minus group, or the aldyl OH, is going to be pointing in the same direction as the original hydrogen. Or in other words, the aldyl OH is going to be pointing in the opposite direction that the enolate is going on. That's probably the better way to put it. This OH is going to be pointing the opposite direction of this. So in the final product, what the relative stereochemistry would be, would be the OH and H pointing in the same direction. And then both portions of the ring that formed pointing in the same direction. So in other words, we get the cis decalin. We get the cis decalin. But does the fact that we get the cis decalin matter in the product? No. It doesn't, right? Because it's going to eliminate anyway, so we lose that stereochemistry. But I just wanted to point out that fact that in intramolecular reactions, when you have an intramolecular ring formation, you will almost always get the cis ring rather than the trans ring. So just to repeat the basic steps of Robinson annihilation, it's enolate formation, followed by Michael addition, followed by second enolate formation, followed by aldol cyclization, and subsequent aldol dehydration. So basically, all the Robinson annihilation is it's a Michael addition followed by an aldol dehydration in the same molecule. So it's a Michael addition followed by an intramolecular aldol dehydration. This is an example of what we call a domino reaction or a cascade reaction, where two different reactions occur back to back. So as I said earlier, if this hydrogen's deprotonated, we get a product like this. What happens if this hydrogen's deprotonated? So if we take this hydrogen, we will get this enolate. Has anyone taken one of these classes with the learning class? The learning class? Yeah, Physics 195 is using it. No, a little bit, you guys, no one's had it yet? The university is really pushing it, and I'm wondering if people like it or not.
What is it?
It's pretty much you do it, the professor makes the lectures ahead of time, and this weird glass apparatus we have at the university, and then puts them up on YouTube. And then the students are expected to watch the lectures from this learning class before, and then the lectures themselves are just kind of like problem solving. Do you think it would work for this class?
No.
Those don't work for any class.
What's up?
They don't work for any class.
Okay, see, they tell us they do, but they need to ask the
Where can I
students.
voice myself about that? Because I'm really against it.
Okay,
Who can
noted. What's that?
Where can I voice myself?
The dean, I guess? I don't know. It's funny.
I think it can work in a small class, but none of the classes I have are less than 100 people.
Okay. We need to hear stuff like this, right? And definitely, stuff that we need to know, so we don't make any bad decisions with your education. So anyway, we get this enolate, and then this enolate here will attack the carbonyl here. Oh, just put sugar and orange. Get this right. Oh, it's a 5-member. 1, 2, 3, 4, 5, 6. There you go. That will give us a ring system that looks like this. So if this carbon attacks, here, let me do it in black. If this carbon attacks here, right, then we have a 1, 2, 3, 4, 5, 6 ring system. Yeah.
So if that's how.
Basically, what I'm trying to show you is why, I'm trying to explain why it goes this way and not this way, because this product's going to be less.
Okay.
That's all I'm trying to show.
Okay.
Because people are going to say, well, why don't we get the other one? And so I'm trying to show you why we don't get the other one. Through this inquisitive, well, what happens if you get it? well, we get them screwed up like this, which is a it's still a 6-6 system, but instead of being a 1-2-6-6 system, it's this 1-3-6-6 system. Yeah.
I'm seeing an added chart in there.
What's up?
Isn't there, because on that one you had 3 bonds before the carbonyl, now you have 4 bonds before with the oxygen.
Let's see. So it attacks here. So this carbon should be linked to this carbonyl. So no, this carbon bound to this alcohol. Then 1-2 carbons, 1-2 carbons. Yes, you're right.
No, you had the right number of carbons, you just put the carbonyl group on the wrong one.
Yeah, shouldn't the carbonyl be at this carbon bound to what was the alkylate? Yeah. 1, 2, 1.
There was just one extra carbon.
Yeah, so it should be this, right? Yeah. Yes, okay. It's still a 6-membered ring. The fact I struggled drawing this should tell you we don't usually draw this because it doesn't happen. But why doesn't this happen? Again, it's ring stability. Why is this ring less stable than this ring? Well, let's draw both of the 6-membered bicyclic systems and ask ourselves, which one looks nicer? Which one looks more stable? So in this case, this one here, this is going to be a cis, it's going to be a cis decalin. So let's draw our chair. Like so. So I guess if I do this, I probably want. Alright, I'm going to draw the alcohol off of this carbon, then it'll go easier to draw. One color. So we have this 6-membered ring. But you know, this looks like your typical cis 6-membered ring, right? It's a 6-membered ring. The important part is, it's a 6-membered ring. It's as stable as you expect a decalin system to be. There's nothing weird about this. You have one axial portion of the ring, one equatorial. It's perfectly stable, yeah.
Oh, could you, by chance, like draw that 6-membered ring as like a chair?
Yes, you could, but I chose the wrong angle.
Oh.
You know, but yeah, you do want to draw. So from the perspective I drew, we're actually looking at this head on, right? And so if you have a chair, so if my hand's a chair like this, and you look at it like this, it just looks like a 6-membered ring, right? But you know, for you, I will draw it as both 2 6-membered rings. So, poorly drawn, but this is basically drawn as 2 6-membered rings. And then now we just have to color code it accordingly. This is actually the ring flip version, my bad, but same idea. Draw this orange. Red. And then there's our carbonate. But the key thing is it's a transdecalin, it's a cisdecalin, sorry, yes, it's a cisdecalin. Cisdecalins are stable. We learned that in Chem 232. And you can draw them where both things are a chair. That's the key thing. You can draw it so that both rings are in a stable chair conformation. It's for this intermediate. In this case, you can't draw it so both things are in a chair. Or more specifically, both of these guys are going to be forced, both of the substituents of the ring are going to be forced in the axial position, right? So when we form this ring, it's forced so that both of these are in the axial position. And so there's going to be this big steric interaction. And so this ring system, and maybe I shouldn't have tried to do this, but basically this ring system, because of this axial strain, is going to be less stable than this ring system. And so even though this can happen, it's just going to do a retroaldol to go back to the starting materials. So again, it's the same idea. The most thermodynamically ring system, and a ring system like this is less stable than a ring system like this. And so what that means is the product we'll get will be this guy. And so I just went through all this analysis just to tell you why we don't depronate this proton. And the simple answer is this proton gives a less stable ring system, even though it's 6,6. Take the picture of this. So once again, the Robinson annulation. Once again, the key thing with the Robinson annulation is it's completely thermodynamically controlled. And it's given us the most stable ring system, which happens to be this Decalin system here, or this Decalin system. So let me give you another example. And this is a classic example. And the reason it's a classic example is because this is the first step of the synthesis of the steroid scaffold. Don't worry about why. So first off, which one of these protons do you think is going to be act as the enolate?
The right one?
Yeah, because it's so acidic, right? So we're forming the sodium enolate. And what's that? So again, the Michael. Here's the Michael product. Once again, this enolate's not going to be reacted because if it adds into this carbonyl, it'll be a 4-membered ring. If it adds into this carbonyl, it'll be a 4-membered ring. So once again, we know the aldol cyclization isn't going to come from this. But we do know, once again, that under ethanol conditions, we can obviously deprotonate this again. And then eventually we can deprotonate this. So we can have a transenolization via protonation and then deprotonation of the other enolate. So you could argue that under thermodynamic conditions, both this enolate and then the other enolate are going to be in equilibrium. Well, I'm just going to take deprotonation event here to give us this. And now I'm going to show you a common modification. So this is the Michael product. And obviously under these conditions we can form the enolate just fine, and you can attack one of these and we go for it. So my question is, under typical conditions, if you form the enolate here, which one of the carbonyls would it attack? Or would it attack each of them perfectly? It can only attack one. Will it attack at one specifically? Will it have no selectivity towards which one it attacks?
Looks the same.
It's the same.
They're the same? Absolutely, they're the same. This is a achiral molecule. It's symmetrical because of this. And so we can attack either this one or this one equal. So one of the dogmas of chemistry is symmetrical things will react identically to either side when it can, unless you have a chiral center. And I'll get to that in a second to prove a point. But yes, so this can either attack this carbonyl and this carbonyl. I'm going to give you the Michael products. And I'll just draw the dehydrated product. So this enolate, I just drew it attacking this one, doing the cyclization and then the dehydration to give us this. Here's my question though, when we do this product, is this a chiral molecule? Yeah, this guy's very chiral. And so we would get this if we just use sodium methoxide and ethanol in one enantiomer, true? Oh sorry, in racemic form. We would get both enantiomers equally. So we would attack this carbonyl 50% of the time, and we would attack this carbonyl 50% of the time. And if it attacks this carbonyl, it will give one enantiomer. If it attacks the other carbonyl, it will give the other enantiomer. So this is a meso compound. Did you guys study meso compounds in 232?
I think so. Yeah.
What's up?
Yeah.
Yeah. So if it attacks this carbonyl, it will give you this product. And if it attacks this carbonyl, it will give you the enantiomer. Don't worry too much about that. I just wanted to point that out, that this symmetrical system attacking either carbonyl will give you two different products. And so I'm not going to test in this, but if you're really curious, prove it to yourself. But I brought this up because I wanted to show you a common strategy for Robinson annulations. And in this common strategy for Robinson annulations, what you do is you take the Michael product. So you do it under mild conditions, so you just get the Michael product, which you can. And then what people do is to push the reaction to completion, they throw in proline. So what happens if you use proline, and we're going to go over the mechanism in a second because it talks about a lot of cool things. Is proline will cause the resulting enemy, and I'll show you in a second, to only attack one carbonyl. So it will favor attacking one carbonyl over the other, and what that means is you end up getting a reaction you end up getting the reaction in high enantiomer purity. So you end up getting it in stereo pure form if you use it. And I don't care about why you get stereo pure form. I just want to show you an application that really draws together a lot of things we talked about in this class. And so if you throw in a secondary amine, we can drive the microproduct directly to the ground cellulation. And so how does this happen? Well, if you have a secondary amine that happens to have an acid in it, what's going to happen? What will the secondary amine that has an appended acid do? No, there's no acidic hydrogen, acidic enough for a secondary amine to deprotonate it. What do secondary amines do when they see lots of carbonyls? What? What do they attack? They attack the carbonyl and form an amine or imine, right? And so if it's a secondary amine, are we getting an enamine or an imine? An enamine, right? So this will give us, and my next question is, which one of these ketones is the amine going to attack? All of them, but which one is it going to favor thermodynamically? Which resulting enamine are we going to get out? The enamine from these ketones or the enamine from the red ketone? The enamine from the red ketone. The way to think about it is these carbonyls have 2 carbon constituents alpha to it. Is that going to sterically hinder attack? It absolutely will. So these carbonyls are sterically hindered compared to this carbonyl because of this substitution adjacent to it. So the product we will get out Yes, I will. I always aim high, right? Is this better? But the key thing is you form a secondary, you form an enemy. And then, what do enamines behave like? Are they nucleophilic, electrophilic? What do they do? They're nucleophilic. Are they more reactive or less reactive than enols? Then an enol, are they going to be more reactive or less reactive? They're going to be more reactive because nitrogen is less electronegative, so those lone pair of electrons in the nitrogen are more freely to donate in the double bond. So enamines are more reactive than enols. So if an enol can do an aldol, can an enamine do an aldol? Absolutely. And so what then happens is the enamine will attack one of the carbonyls. Double attacks on the carbonyls in an aldol type reaction. And then, what happens if you take an enamine and you add acid and water? Sorry, what happens if you take the resulting iminium from this attack and you add acid and water? It's going to hydrolyze to go back into the ketone. Alright, furthermore, we formed this system, but we're still going to be under acid and water. What's going to happen if we're still under acid and water? Once we go back in the imine to the ketone again. Well, we're going to do an acid catalyzed aldol dehydration. Right, a couple things will happen. First thing, under acidic conditions, this ketone will favor the enol form. And where it can do both enols under strong objective pathway enol. By the way, what about Steph Curry last night? I scared my wife with my reaction. Yeah.
Did we lose a methyl?
Did we use a method? Yes, we did. Good eye. So this is the enol, also under acidic conditions. Well, I was going to protonate this. And if this is protonated, this can leave. Don't want to forget the methyl this time. Giving us a carbocation that's adjacent to an enol. And of course, we have a carbocation adjacent to an enol. Again, this is just the acid catalyzed dehydration aldol mechanism. But when it's said and done, that gives us the final product of the Robinson annulation. So really the take-home message from that is, if you have a Michael product, you can catalyze the enol with secondary amine. And this reaction became the linchpin of steroid synthesis because they found out if you use proline, you could do this enantioselectively, so you only make one enantiomer. And it happened to be the same enantiomer that was in steroids. And so people would make this, and this is the #1 synthetic intermediate to make steroids. And so if you make this, you can make pretty much any steroid you want in 4 or 5 steps. So the San Francisco Giants in the early 90s have a lot to thank photosynthesis. Although he was just found, they threw out that case in court, so yeah.
Professor?
Yes.
On the top line in the 3rd step, what happened to that oxygen on the double bond?
This one or
No, the one before it?
right here?
Yeah.
This oxygen.
Yes.
Just enamine formation. So I said we don't want a secondary amine. Want the secondary amines to the carbonyls, they form enamines. So through the enamine formation mechanism, the amine adding in, and eventually kicking off water to give us the imine. And then, since it's an iminium, then you form the enamine. So, I spent this entire lecture talking about various variants of the Robinson annulation, but the same thing is true. It's just 3 straight reactions. It's a Michael addition, followed by an Aldol addition, followed by a Robinson annulation. So people will, I'll give them a product, and, I might give you something that looks like this on a test. And ask for a product of the mechanism. And people usually freak out. Like, oh, well, we can do a Michael addition, but then what? But really, it's just a thermodynamically controlled Michael addition followed by a thermodynamically controlled aldol cyclization to give the most stable ring system, followed by a dehydration to give the product. So the Robinson annulation isn't that scary. It's just 3 reactions we've talked about a lot, just back to back to back. We'll talk about the Matic reaction next week, and then I'll do a quick important stuff for chapter 20 the rest of the week.